Hello friends, welcome to engineering tutorial. So we'll continue our discussion with the application of Thevenin Theorem to circuits involving dependent sources. This is the second question which we are going to discuss. So again we have this circuit. It consists of an independent voltage source 6 volt, some resistors 5 ohm, 3 ohm, 4 ohm connected in the way they are, and we have a dependent source which is a current dependent current source. Okay, it is dependent on this current flowing through the 3 ohm resistor. Now our objective is to find VTH and RTH. So VTH is nothing but this voltage, open circuit voltage across these two terminals. So again here we have to use the mesh analysis technique. So let us assign the mesh currents. This is say I1 and let's say this is I2. So here some important things are there. First is identifying the value of Ix. Here I2 is equal to Ix. That is the first relationship. Next is that VTH is 4I2, the voltage drop across this 4 ohm resistor. So VTH is equal to 4I2. So all we are interested here in this circuit is to find the value of I2. Okay, so let us write the KVL equations. Another thing to notice here is that these two meshes they have a current source in between. It is an independent current source of course, but it is a current source. So when two meshes have a current source in between, it is called as a super mesh. Okay, super mesh means these two meshes are combined. The KVL equation is written for the two meshes combined. So the equation here is 6 minus 5I1 minus 3I2 minus 3I2 minus 4I2 is equal to 0, or we can write it as 5I1 plus 7I2 is equal to 6. This is the third equation. And another important equation is the auxiliary equation correlating the two mesh currents. Here this current source, it has a value 1.5 Ix or 1.5 I2. I2 is equal to Ix. The direction of it is upward. Here through this I1 is flowing downwards. See, let me draw it here to make you understand in a better way. Here this is the dependent current source 1.5 Ix. As I2 is and Ix, they are equal, so it is, we can write it as 1.5 I2. Through this I2 is flowing upwards, I1 is flowing downwards. So we can write this as 1.5 I2 is equal to I2 minus I1. Why? Because 1.5 I2, this dependent current source, has a direction upwards. So the upward moving or upward flowing current will be considered as the reference, the predominant, and I1 will be the other, I2 minus I1. 1.5 I2 is I2 minus I1, or the value of I1 is equal to I1 is minus I2 by 2, which is equal to 0.5 I2. if we take I2 towards the left hand side, 1.5 I2 minus I2, which is 0.5 I2 is equal to minus I1, or I1 is equal to 0.5 I2. So this is the fourth equation. I1 is equal to minus 0.5 I2. So now we will substitute the value of I2 here in place of I1 and we'll get the answer in terms of I2. Okay, so let us do that. So substituting this I1 is equal to minus I2 by 2 here, we will get 5 into minus I2 by 2 plus 7 I2 is equal to 6, or it will be, if we took 2 as the LCM here, a little bit upwards, okay, 2 minus 5 I2 plus 14 I2 is equal to 6, or plus 9 I2 is equal to 9 I2 by 2 is equal to 6, or I2 is equal to 12 by 9, which is equal to 4 by 3 ampere. I2 is equal to 4 by 3 ampere. Now VTH is equal to 4 I2. Okay, so VTH here will be 4 into 4 by 3 volt, which is equal to 16 by 3 volt. So if we calculate 16 by 3 volt, it will come around 5.3. Let me calculate, it is coming around 5.33 volt VTH. So the value of VTH we have got, okay, which is 5.33 volt. So the important thing here is first identifying the relationship between the dependent source and the circuit parameters, the mesh currents. So here first we identified that I2 is equal to Ix. Then we wrote the KVL equation for each mesh, where it was a super mesh, so one KVL equation. Then is the value of the dependent current source in terms of the mesh currents, the auxiliary equation, which we got this relation, I1 is equal to minus I2 by 2. Then we substituted this value in the original KVL equation, the main KVL equation, and we got the value of I2, which was required to determine VTH. 4I2. So we got the result, 4I2 is 4 into 4 by 3, which is 16 by 3, which is 5.33 volt. Okay, so you have got VTH. Now let us calculate RTH. Okay, so now comes the second part of the question, which is the calculation of RTH. So in normal independent source circuits, what we used to do, we used to deactivate the dependent sources, that is short circuiting the voltage source, open circuiting the independent current source, then calculating the equivalent resistance across the terminals. But here in this circuit we cannot do that, it is not that straightforward because of this dependent source. In question 1 we discussed one method of determining RTH, here we will be discussing another method. So for that we have to deactivate this voltage source, means short circuiting it. Okay, we have short circuited it, and we have to excite this circuit with a unit current source, 1 ampere current source, because there are no independent sources present. In the previous question we connected a 1 volt voltage source, here we are connecting a 1 ampere current source. Our objective is to find the voltage across this current source, let us call it V0, and RTH will be this voltage V0 by 1. This is in volt, this is in ampere, that will be the RTH. Okay, this is the thing here. So our objective is to find V0. Now here looking at this circuit, mean we can use nodal analysis method here. Nodal analysis. V0, here it is there, the voltage across this current source, no resistor, so here also it will be V0, this node. Here in between these two nodes there is a resistor, 3 ohm resistor, so this node voltage will be different, let us call it V. Okay. Now let us connect the ground for our reference. We know there is always a ground present, but in nodal analysis always having a ground gives us some clarity, it does not cause any unnecessary confusion. So now we have to write the nodal equations. Another important thing, this is Ix, okay, I missed out this is Ix which is given in the question, Ix. So another important thing is to define Ix in terms of this circuit. Here Ix is this node potential minus this node potential divided by 3. The current is flowing from this node to this node, so it is V minus V0 by 3 ohm. Okay, this is equation 1, this is equation 2. V minus V0 by 3 ohm, higher node potential minus lower node potential by resistance involved. Okay, so now let us write the nodal equations at this node, node V, nodal analysis at V, this node. Let us consider this as the outgoing current, this is the incoming current, Ix is the outgoing current. So this nodal equation, it will be V minus ground, ground potential is 0 by resistance involved which is 5, this is outgoing, Ix is also outgoing, so Ix is V minus V0 by 3, so it is plus V minus V0 by 3, and another one is this is the incoming current, so that is 1.5 Ix which is nothing but 1.5 into V minus V0 by 3. This is the nodal equation. Okay. So now if we simplify it, it will become V by 5 is equal to V minus V0 by 3, that is 1/2, this is a 1 by 2, which is nothing but V minus V0 by 6. V by 5 is equal to V minus V0 by 6. That implies cross multiplication 6V is equal to 5 into V minus V0, which is equal to, that implies 6V minus 5V is equal to minus 5V0. That implies V is equal to minus 5V0. This is another important relationship, the third important relationship. V is equal to minus 5V0. Okay, so please watch the videos related to nodal analysis which I have posted in my channel. Okay, there I have explained in detail about nodal analysis, how to write nodal equations. That's why I have not got, I have not discussed in detail how I have written this nodal equations. Okay, I have discussed that in the videos related to nodal analysis, so please watch those videos first. So this is the third important relationship which we established here. Now we will apply a nodal analysis at this node to get the second nodal equation. So nodal analysis at V0 node, at the output node here, at V0. So here Ix is the incoming current to the node. Let us assume that this is the outgoing current. 1 ampere is also the incoming current flowing into the node. Ix is flowing into the node. So we can write here Ix plus 1 is equal to this current, which is V0 minus ground potential, it is 0 by 4. Ix we can replace it with this V minus V0 by 3, V minus V0 by 3. Okay, so now we can write it as, that implies, taking the LCM, 3 V minus V0 plus 3 is equal to V0 by 4. Okay, or we can write it as, that implies V minus V0 by 3 minus V0 by 4 is equal to minus 1. Okay, or we can write it as, taking 12 as the LCM here, it would be 4 into V minus V0 minus 3 V0 is equal to minus 1. That implies 4V minus 4 V0 minus 3 V0 is equal to minus 12. That implies 4V minus 7 V0 is equal to minus 12. Now V is equal to minus 5 V0. So, we will substitute that, V is equal to minus 5 V0. So, it will be 4 into minus 5 V0 minus 7 V0 is equal to minus 12. So, it will be minus 27 V0 is equal to minus 12. That implies V0 is equal to 12 by 27, which is equal to 3 is 4, this is 9, 4 by 9 volts. V0 is 4 by 9 volt. Now, the relationship which we got, that is, this is the fourth equation, RTH is V0 by 1 ampere. V0 by 1 ampere. The voltage across this 1 ampere current source, this is the current flowing away, the supplying the output voltage. So, RTH is V0 by 1 ampere. So, RTH will be 4 by 9 by 1 volt by 1 ampere, which is equal to, let me calculate, it is coming 0.4444 something ohm, or we can write it as 444.4 milliohms. That is RTH. This is the value of RTH. So, here this is the second method of determination of RTH. In the previous question, we connected a 1 volt voltage source across the terminal across which RTH was to be found. We found out the current supplied by that 1 volt voltage source. RTH was 1 volt by I0, the current that was supplied by that voltage. Here we have connected a 1 ampere current source, and we have to find the terminal voltage across these two, the ends of the current source, and RTH is V0, the terminal voltage across the current source, by 1 ampere, which is the known thing. In that case 1 volt was known, here 1 ampere is known. In that case voltage was known, in this case current is known. Okay, RTH is this. So, this is the second part of the question, calculating RTH, and we have done it. So, both VTH and RTH we have calculated. VTH we found was around 5.33 volt, 5.33 volt, RTH is 0.444 something ohm. Okay. So, this is the second question related to Thevenin theorem involving dependent sources. So, I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.